Welcome back, everybody. We've been talking about Neyman-Pearson for a while, but we haven't actually said what it is. And so this is, in my opinion, the most contentious thing in statistics. Saying that, the version of Neyman-Pearson I'm going to tell you about today, I don't disagree with at all. There's a controversy in statistics about the utility of p-values, what they are not. Neyman-Pearson is kind of the backbone of the whole structure. Fisher introduced the p-value to us. And basically, he said, look, there's a probability of more extreme data, this thing that maybe you've learned about in Stat 101, I'll say a little bit more about it on Monday. Probability of more extreme data given the null hypothesis is, evidence against the null hypothesis of that number is small. So small probability of more extreme data, i.e. your data lives in a very extreme part of the space, given that the null hypothesis is true. If it's small, that's evidence against the null hypothesis. That's what Fisher said. Fisher's wrong. So it's true in some cases, but not in all cases. Neyman and Pearson wanted to give this some real meaning. And so what Neyman and Pearson said is they introduced the idea of an alpha level. So some level of a test, and if your p-value dumps the alpha level, then you reject. And what they ended up saying is that the alpha level is the probability of the type 1 error. And under the Neyman-Pearson lemma, if you formulate your test statistics correctly, i.e. through the likelihood ratio test, that's going to minimize the type 2 error. And so Neyman and Pearson thought they were doing Fisher a great service by giving a real frequentist interpretation of the p-value. So probability of more extreme data given the null hypothesis, what is that number? What does it mean? And so that thing, if you get a p-value that's like 0.02, what is that? What does it actually mean? It's not the probability of a type 1 error being 0.02. The threshold is the probability of the type 1 error. So if you ended up pre-specifying my alpha level is 0.05 before I even begin, and I see a p-value of 0.02 and I reject, your type 1 error rate is supposed to be the alpha level, 0.05. Fisher hated this. And he hated it because you had to pre-specify alpha to do it. And so you will hear from your Stat 101 teachers, well, the idea is if you have pre-specified your alpha level at 0.05 and your p-value is 0.02, then your type 1 error rate would be 0.05. But if you had pre-specified your alpha level to be 0.1 and you saw your p-value of 0.02, then your type 1 error rate is 0.1. And Fisher obviously saw the issue with this. You have to pre-specify for that to be true. And nobody in this room does that, I don't think. So you see a p-value of 0.06 and you go, well, maybe I'll make my alpha level 0.1, so then I can say something about it. So it's this hypothetical sort of thing that Fisher didn't like. Neyman and Pearson never actually employed the Neyman-Pearson lemma the way that we do, i.e. we assume we pre-specify maybe 0.05 and then you just reject it accordingly. They never did that. So there's not a single paper they wrote where they do that. You see this going on in science all the time. And so what I want to tell you about today is what Neyman and Pearson showed us. I want you to understand it. And then next week we'll spend a little bit of time talking about what do you actually do. Lots of issues here. I'm going to try to make the conclusion about this class something about estimation. Estimate if you can. We spent a lot of time talking about estimation techniques. And we spent a bit of time talking about some decision theory. So when you're estimating something, you have some sort of optimality criterion that you're aiming for. I want to minimize the risk function under an L1 loss function, something like that. So that I think is coherent. That stuff makes sense. What you're trying to do, of course, coming up with your objective function you know, that's a subjective choice that you're going to make. And so, but I think we can all do that. Estimation makes sense. A lot of branches of statistics kind of agree in estimation, but for testing purposes, a lot of times we disagree with each other. In the simple setup that I have right here for Neyman-Pearson, this is called the simple versus simple hypothesis. This is just a data point, and this is another data point. Or this is just a point in space, this is another point in space. This could be 3-dimensional or 10-dimensional, but it's just a point in that space. So we're going to test 2 different points in the space. Things go wrong when we start making this the sharp test right here simple, and then we make this composite, i.e. it's maybe an interval or something like that. So that's where everything's going to fall apart with Neyman-Pearson. For the simple versus simple case, I think what they did is reasonable. So, and in fact, I'll even allude to a Bayesian would agree with what Neyman-Pearson did. It's the extension of this in the simple versus the interval, something like that. That's where everything is going to go wrong. What Neyman-Pearson do say about the error rates is almost true. We have to add another condition for the sharp test that everybody disagrees on. I think we should stop doing that. But I think for at least our literacy, we need to understand what they say. And then you guys are going to have to make choices when you end up doing analyses as to what you want to do. P-values are starting to be banned by certain journals. So there's an article that I put up on the web page that discusses this, that a journal a couple of years ago banned p-values from their journal. It's kind of interesting. I don't think they should have done that either. You know? So we'll look at that editorial, but if you want to read it over the weekend, it's just a page long. The ASA came in, the American Statistical Association, and said, well, we need a commission on this so that we can advocate to people that are doing statistics. And they put together 2 groups. They put together the frequentist group, the Neyman-Pearsonians, and they put together the other guys, the Bayesians, right? That's how everybody likes to partition so cleanly like that. And basically, through these consortiums, and I put a paper up online that goes through what they advocated and what the 2 commissions found, is that still everybody disagrees. So nothing happened. What they ended up advocating, I almost agree with the frequentist group a lot more than I agree with what the Bayesians ended up advocating in that article. So it's still a mess. You know, what do you actually do? So lots to consider right here. I'm not sure we'll be able to do this complete justice in 3 days, but we'll try. So over the course of graduate school for you, if you ever want to talk about this stuff more and more, happy to talk about it. I talk about this in my Bayes class as well. And what I usually end up doing in my Bayes class is saying, well, let's at least apply this to high-dimensional problems, see what goes on. So I'll give you some computational tools that stem out of all of this too. So, you know, maybe some of it we can use, but there is a lot of debating going on and it concerns this. So probably means there's something wrong. And I'll tell you what's wrong on Monday. Saying that, this is not a hard decision to like comprehend. It's like either I think theta is theta naught or I think theta is theta. So this is a simplified version of everything. And I think in this version, things do not go wrong. Okay. Also, I've got some homework problems out for you. I gave you about a dozen problems. I think maybe there's 11. Some of them are real simple. You know, they're early chapter 8 problems. So work through those, and it'll have you work through like computing power functions and stuff like that. I'm going to give you a final exam on the 11th. That's our time for the final exam. I'm going to make it a take-home. This will be take home. And I thought I would extend the due date to kind of the last possible minute for me to grade. So I've got to get my grades in on Friday. This is a Tuesday. This is a Thursday. So if you have the exam and all of these homework problems sent to me by p.m. on Thursday, I'll be able to get all my grade on time. So try to aim for that. If you have any extra credit problems, if you did some of the computational assignments, you can turn them in at the same time. So I'll probably make the final 6 problems, something like that. So nothing overwhelming. And for those of you that are first-year students in the statistics department, I'll try to add a few problems in there that'll prep you for my questions on the qualifying exam. I know even just saying the word makes you tremble. So anyway, I'll try to prepare you for that. I'm going to ask a few little decision theory questions, so I'll try to give you some practice with those. There's also some practice in the problems that I posted on. Next Thursday is reading day. I'm going to do a review session for you guys on that Thursday if you guys would like. So there's extra questions. So we'll come back on reading day, same time, same place, same strategy. Okay, let's jump into Neyman-Pearson. So I want to just define a few things for you before we begin. So these are just definitions. Uniformly most powerful test, UMP. You hear people talk about it all the time. What they're saying is that a uniformly most powerful test, that's going to be this one. This is the UMP, or the UMP test. A UMP test has the property that the power is higher than any other test. So this is any other test. And we're going to be specific about this, that the UMP test is that the power function is higher in the alternative space. So keep in mind, power is 1 minus the type 2 error rate when you're in the alternative space. So I'll just write that down. 1 minus the type 2 error rate. So uniformly most powerful tests have the property that the type 2 error rate is smallest. Okay, so the power is highest in the alternative space. So power function is the probability that you reject. So you have some tests, some criterion for rejecting. You want the type 2 error rate to be small. So, okay. So that's what a uniformly most powerful test is. It's the test that minimizes the type 2 error. That's the idea. Here's another couple things. This is going to pertain to the null space. So this is all about the alternative space. Alt space. And for the null space, we have a couple definitions that we're going to work through. It's the probability of rejecting. So this is my rejection region. So that might be the thing defined by a likelihood ratio test. So if I end up coming up with a threshold, then I've defined a rejection region. So there's 2 definitions. We're really going to stick with this one. But we'll say a few things about this right here. So a size alpha test is such that the probability of being in the rejection region is alpha. And that's in the null space. So when I'm computing under theta naught. And we can also think about a concept called the level of the test. And that's just bounding the test. So if we weren't working in a simple versus simple case, this is a useful idea to us, that we can bound the type 1 error. So this is a bound on the type 1 error. In the simple test that we're going to discuss today, the level of the test is the size of the test, because there's only one point. So there's not other points to consider in the null space. There's only one point. So I compute it, and we're going to say that it's alpha. We're going to bound everything by very typically people take alpha to be 0.05. This is the threshold that Neyman-Pearson are working with. So I'll just say that. This is the threshold on the type 1 error. In the book, they end up jumping between these two concepts. But the reality is because they're dealing with a simple versus simple thing, you could substitute in size without any loss of, nothing will be lost in the proof. I'll say a little bit about this while we go through the proof. But if you would like on your first reading through the proof to just insert size and not think about level, that will work. Okay. So I'll point out where this distinction is made in the proof. Okay, so we have two concepts. And this is what Neyman-Pearson are working with. They're going to bound the type 1 error, and then they're going to show which criterion gives you the uniformly most powerful test. So it would be very nice if you could minimize the type 1 and type 2 error simultaneously. You cannot do that. There's a trade-off between. Okay. So now I need to tell you what Neyman-Pearson actually said. So there's a little bit to chew on, but it's not that complicated. So let's just write down a couple of conditions. So I'm going to say, here's some conditions. There's going to be two of these, 1 and 2. And then we'll have some results over here. So, Neyman-Pearson. So based off of these conditions, Neyman-Pearson will say something. Okay. So, condition 1. So, I'm going to I'm just going to write this down. So I'm going to consider some tests. This thing right here is just going to be an indicator function on whether or not I reject. So this is going to be X is in the rejection region. This is X outside of the rejection region. Okay, so my test is just going to be a switch. So it's going to tell me whether or not I reject. Okay, so if this thing is a 1, then I've rejected. Otherwise, I don't reject. My rejection region is going to be specific. So this rejection region is going to be this thing. This is going to be F X given theta 1. Let me make sure I get my direction right here. K Fx given theta 2. So that's going to be this right here. So this right here is going to be my rejection criterion. We'll talk about that for a moment. When I fail to reject, I do the opposite thing. So that's going to be f of x given theta 1 is going to be less than k fx given theta naught. You might be asking, where's the equal sign in all of this? I'm going to write it down exactly the way the book did it. So they end up letting k be greater or equal to 0. So the equal sign appears when k is equal to 0. So that's where the equal sign is in basically I just have this criterion. There's some weird criterion, maybe you know this criterion already and you recognize it, but it's a criterion for rejecting. So what I'm going to do is I'm going to collect my data. So I've got my data right here. I'm going to plug in my two hypotheses, those things, and I'm going to have some threshold k in here. So I just pick some number that's positive. Maybe that relates to something for us. Right now you can think about it as fairly arbitrary. And I plug everything in and I can check this condition as to whether or not I want to reject or not. Okay. The second condition is going to be that the probability of x being in the rejection region under the null space. So a lot of times I write this like this. That's the null hypothesis. This is going to be equal to alpha. Okay. So this is the size of the test. This is a size alpha test. So this test, this little switch, we're going to make size alpha. How do we do that? We actually pick a k to do that. K is the value that's going to do this. So what we're doing with this is we're saying the probability of the rejecting incorrectly. So if the null is true and I reject, I just made an error. So this is a type 1 error. So what I could do to do this is I could look at this criterion right here. I could just keep sampling data from whatever my model is in the first place. So my model is going to be this stuff right here. So x is coming from fx given maybe theta naught. So what I'm going to do is I'm going to sample data out of this model. So I'm going to sample it under the null, and I'm going to wiggle this k around until I find that alpha of my samples were rejected incorrectly. Let me just say that again. So just to get an idea here, is I'm just going to sample a data point right here. I'm going to do it over and over and over again. So let's say I have a collection of 100 x's. They all came from the null model. I'm going to budge this thing around such that, let's say this was 0.05, such that 5% of the x's get rejected incorrectly. They all got generated from the null. That's the idea here. So I can find that k if you told me this model and you told me what those hypotheses were. So this is going to calibrate k for us. So I'll just make a note. K depends on this. So we're going to pick our k such that this is a size alpha test. Does this criterion look familiar to you? Let's just look at it. So x, element to the rejection region, is f of x, given theta 1 is greater than k fx, given theta naught. Keep in mind, k is greater or equal to 0. Have you ever seen this before? Bunker.
Is it like the likelihood ratio, or is it similar?
It is, yeah. It's exactly the same as the likelihood ratio test. So the likelihood ratio test, what we wrote down before, and it's kind of unfortunate that the book jumps around these different definitions that are all exactly the same. But what we did is we looked at the maps, theta in the null space, my likelihood function. I'll just write down that function to look like this. The likelihoods in the sampling distribution have exactly the same form. I'm going to be treating it as a function over theta. And this is going to be a max over the entire. over everything right here. Fx greater than theta right here. And we're going to bound this by C, and this thing was an element between 0 and 1. If you rearrange this a little bit, you can come up with this same exact criteria. They flip the sign around on everything, so they're putting the fx given theta 1 over fx given theta naught. They're saying this is greater than k right here. But k is going to be some positive number right here. Anything positive. I can flip this ratio upside down, play around with my k, and come up with a criteria that looks very similar. So what I'm doing is I'm looking at this ratio right here and I'm bounding it, which is essentially the exact same thing as bounding the likelihood ratio. Let me just ask you a question. Where are my maxes in all of this? I don't have a max in here.
Because it's a point?
Because it's a point. So it's just a point. You don't need the max, you should just plug it in. Let me just point out that this is the likelihood ratio test in disguise. So it's the exact same sort of criteria that I'm comparing the ratios under two models, and I'm coming up with a bounding condition on it. So this and this are one-to-one with each other. One of the problems in the book helps you to understand this. So one of the homework problems that I gave you. Okay.
But under the likelihood ratio test, wouldn't the denominator be the maximum under theta 0 union theta 1?
Yeah, so I changed out the condition a little bit and taken out the union right here.
Okay.
So you could end up just, instead of doing that, what you could do is you could let this be an element of just H1 right here, but then I wouldn't have that criteria that this is bounded between 0 and 1. It would go off between 0 and infinity.
Okay.
So, and this is just flipping the thing upside down. So same criteria. So I think they put it in the book that this is a over the union, because thinking about things between 0 and 1 is maybe a little bit more to it. So, but they're just taking out the union and then bounding it by something that can go off to infinity. They're flipping everything upside down. The numerator and the denominator switch rules in all of this. So it's just a mental exercise to think, oh, these are the same thing. I'll also point out that in this condition right here, when we're just doing a simple versus simple thing, this is also equivalent to the phase factor. I'm integrating over a point, which is the same as maximizing over a point. So this condition right here in the simple versus simple case, not in composite cases, but in the simple versus simple case, this is the likelihood ratio test in disguise. It's also the phase factor. So everybody can agree for a moment. So I'll just say equivalent to the likelihood ratio test, stat, and the phase factor. Kind of nice. If I'm integrating over a point, that prior distribution is not going to make any difference to us. I'm just evaluating under one point. So that's nice. I like that. Okay. So these are the two conditions. The test is the likelihood ratio test stat, and it's calibrated to be size alpha. So I pick K so that my likelihood ratio test stat, that thresholding has a type 1 error rate of alpha. That's the idea. So with 1 and 2 are true. If 1 and 2 hold, then we're going to say two things, A and B. let me prove the first part, or the second part right here, size alpha. How do I prove it? It's told to us. It's size alpha. So our test is size alpha. We'll need a proof to show that this test is UMP, uniformly most powerful. So if I adhere to the likelihood ratio test stat, just written in a slightly funnier form than we wrote it before, the test is UMP. So then I'm going to say if a UMP test exists, it is delta x. It's this test. So what this part says is that there's no other test that does this. This is the only one. So this is the sufficient condition, this is the necessary condition, if you want to think of it that way. So this is an if and only if statement, is what that is. So we're going to do this proof right now. We'll come back next time and we'll do this one. They're basically the same proofs. So if you understand this one, you'll understand this. We're just going to unpack it and show there's only one test that can do this. So let me just recap. If we follow the likelihood ratio test stat, i.e. we're bounding that thing and we pick our threshold such that the test is of size alpha, that test is UMP. If anybody else has a UMP test, it is equivalent to this one. Okay, so the whole p-value gain is equivalent to likelihood ratio tests, things. So what you end up doing is you threshold that test statistic that you get out of the likelihood ratio test statistic. So we looked at a couple of examples of how we get those rejection regions. Okay, let's prove it. So we'll prove A, and we'll come back next time and prove B. Give you a chance to read through the proof at home, see if you understand what we just went through. It's usually hard to understand a proof if you're just sitting here at 9 o'clock in the morning. We'll come back next time and discuss it a little bit more. Then I'll tell you some of the extensions people have tried to extend this to, and that's where we all fight with each other. So I think the key to making this not a fight in the future is that we at least understand what Bayesians are doing and what non-Bayesians are doing when Neyman-Pearson is reasonable and when it might not be. So we need to look at a couple different cases. Let's do proof. Your proof of A. So we'll show delta x is UMP. We've already shown that it's size alpha because it's just the condition. Let's make a note. It's of size alpha. Okay, here's the master equation for understanding this proof. So I'm just going to write it down. Here's my master equation. It's not called the master equation, and there's nothing called the master equation. I'm just going to call it the master equation so that you know it's really important. So this is the equation you need to understand. I called it an equation, it's actually an inequality. So this is going to be delta x minus delta x star. I'll tell you what delta x star is in just 1 second. This is going to be f of x given theta 1 greater than, say, minus k fx given theta naught. this is going to be another test. So this is going to be any other test out there, not the test that we just picked. So our test is based off of the likelihood ratio test stack. So you could imagine another test out there. So let me think about not using the likelihood ratio test stack. Maybe I do something like this. So, for example, I could think of about an infinite collection of these. So maybe I look at f of x, given theta naught, subtract f of x, given theta 1. If this thing is negative, less than 0, I'm going to reject it. So i.e., this thing is bigger than that. Theta 1 is more compelling because its likelihood function is bigger. So you might ask, why do we like ratios? It's this Ump thing. And all the arbitrary constants cancel out. But this is a different criterion. So this is an additive criterion. And this is a worse criterion to use. It probably will work if n was really high or something like that. So the ratio test is better. Okay. You can imagine lots of different testing criteria. So any other test, right here. So it's going to be a 1 or a 0. And it's going to be testing the exact same thing. So this test is also testing this. And it's also going to be size alpha. The book says let this be level alpha. So I'll write it down as level alpha, and then I'll discuss it in the proof. So some other test for, again, this stuff over here. Star. And we're going to let it be level alpha. If you'd like to think of it as size alpha, you can do that. It's not going to contaminate the proof again. But we can see a few extra things if we let it be level alpha. Okay. So let's look at this. Can you see instantaneously that this is true? I think when I first saw this in the book, I was like, why is that true? And so they just state it. They say this is true. Let's look at it. Let's imagine this thing was a 1. So if this was a 1, this is either going to be a 1 or a 0. So this is either going to be 1 minus 0 or 1 minus 1. If this was a 1, right here, this is true, because it's going to be equal to 0. If this is a 0, however, this thing's going to be positive. It's going to be a 1. And then we have to just think about this right here. And so if this is a 1, we reject it. When do we reject? When this is true, right here. So if this is true, this is positive. If x is an element of R, i.e. delta x is equal to 1. So this is positive. If this is a 1. If this is a 1, this thing is 0. If this thing is a 0, this is a 1 times something positive. So that's all true. Let's do it where this is a 0. If this is a 0, then x is not in the rejection region. If this is a 0 right here, then everything is equal to 0. It doesn't matter what I multiply 0 into, it's still 0. However, if this is a 1 right here, then this thing is going to be negative. But if this is a 0, then x is not in our rejection region. And this thing right here is going to be a negative. Because the sign flips the other way. So now we verify that equation is true in all cases. I'll let you think about that, but that's true. So once we have this, the proof is relatively straightforward. So I'm just going to carry this through. We're just going to integrate over this. So 0 is going to be our bound, and I'm just going to integrate everything that I wrote down in my master equation. Delta x minus delta star x, fx given theta 1 minus k fx given theta naught. Yes. That's still true. That thing's always positive. When I average over it, it's still positive. When I integrate over it, just think of that as an averaging. Okay, so there's 4 terms. There's 4 integrations, and they all kind of look like this. So I can break this into 4 things that all kind of have this same form right here. Delta x. So let's just talk about the first one. So if I multiply this with that, I just treat that integral separately. So fx given theta 1 dx. This thing right here is the expectation of the indicator. And I'll say that theta 1 is true. So this is x given theta 1 right here. So this is the probability. So expectations of indicators are probabilities. If that's confusing you, think about Bernoulli distribution. So Bernoulli, the expectation is P is the probability of that event. So this is going to be the probability that X is going to be rejected. That's what my test is. And this is going to be under theta 1. So this is the probability that I reject. That's what the switch is. It's telling us to reject. So this is the probability statement of this thing. That's this delta x is an indicator of whether or not that's true. This is the power function for theta 1. This is just power. So this integral is going to break into 4 power functions. I'll just write them down. This is going to be b theta 1 minus b star theta 1. That's for this test right here. Actually, yeah, that's okay. Minus k b theta naught. Get rid of this. Minus b star theta naught. So when I work through these 4 integrals, this is what I get. Any questions? So pretty simple. We're getting really close to having this proof. So somebody help me out. What is this? It's alpha. So this is the power under theta naught. It's alpha. So why? That thing is given to us. This thing right here, if you want to take the book suggestion and say that this is less than or equal to alpha, i.e. it's level alpha, we could make this size alpha. If this was size alpha, this whole term would be 0. If it were level alpha, i.e. I'm considering a test with an even lower type 1 error rate. What I'm going to do is I'm going to increase the type 2 error rate for it. It's only going to have more type 2 error if you do that. You're never going to decrease the type 2 error by decreasing the type 1 error. That would be nice, but it doesn't happen that way. So you can consider any test with lower power than this, or in the null space, lower type 1 error, and all of our statements are still going to be true. I'll say that again in a second. But this whole term right here is either 0 or it's positive. So this is positive right here. So this is going to be less than or equal to, because this is a negative thing. This is also positive. So I'm subtracting off something that's positive. So this is going to be b theta 1 minus b star theta 1. And that's going to be true in any case. So I can consider tests that are smaller type 1 error rates, and I'm only going to increase the type 2 error. Or I can consider a test that is exactly the same size. And the proof will work out either way. Ultimately, we've just proved our point. So what we just wrote down when I rearrange everything, on the other side of this 0, so I'm just going to pull this over to here, and our proof is finished. So b theta 1 is greater or equal to b star theta 1. If we go back to this condition on what uniformly most powerful is, this is it. So we're UMP. Yep. Delta x is UMP. What's delta x? It's the test pertaining to this criteria, where I've chosen k to satisfy that. So uniformly most powerful. And I don't think that that's a bad thing. This criterion makes sense. And so this is a good thing that Neyman-Pearson did to us. Just that everybody misunderstood and started extending it without thinking about it. So next time we'll come back and we'll do the other direction, but let me say a few things about this first. That the way there's a homework problem that I assigned to you that covers this. And as you think about everything, that if I ended up taking theta naught to live in an interval or something like that, and so if I ended up considering this test, so if I did the one-sided test, everything Neyman-Pearson said holds, and it's reasonable as well. That I could just consider theta naughts marching in a direction and consider these things going in a different direction. So I can compare any point in this space to any point in this space. And the whole idea here is noting that this function right here, this thing is monotonic. So it's going to end up giving you a likelihood ratio test that's monotone. That if I keep increasing theta naught, this thing is either going to go up or down, but it doesn't go up and down. It only goes in one direction. There's more and more evidence if I start moving farther away from theta naught. The trouble is, in Neyman-Pearson, is when they consider this test right here. I.e., I move to the right and the left of theta naught, and the likelihood ratio test statistic is not monotone. So it goes up and it goes down as I scroll over the alternative space. That's not a coherent rule. So that's really problematic. We'll talk about that next week. Danielle, you got a...
Yeah, just to be clear, the Neyman-Pearson still holds for both directions of one-sided tests?
Yeah. So, yeah, exactly. So for the one-sided test, I think Neyman and Pearson came up with something reasonable. Simply, and I want you to think about this over the weekend, that if you do it in the sharp test when you're comparing a point to the continuum, this likelihood ratio test stat goes up and it goes down. And that's weird. So you shouldn't have non-monotonic rules. Saying that, Neyman and Pearson do show that for a bounded array, this is uniformly most powerful. So what they end up needing to impose is another condition to make this all make sense. We'll come back and we'll talk about that condition. But ultimately, I think what Neyman and Pearson said for the simple versus simple case, a Bayesian would agree with them. They're using Bayes factors, doing the same sort of thing. We all agree with each other. In the one-sided comparison, Bayesians and non-Bayesians are close to each other. And oftentimes we're in the same ballpark. In the sharp test, and it has to do with the non-monotonicity of this function that you're using, we don't agree with each other though. So I'll let you chew on that. We'll come back next time, do the other direction of the proof, and I'll try to fill in as much as I can about this debate. So also maybe you want to read the statements that I put up online. If not, we'll glance through them. I've highlighted them. So we can look at a few of the passages and see what people are talking about. This is going to be the biggest black eye for statisticians 100 years from now. People are going to go, why did they do this? So the machine learners, the people in computer science, they got it right. Where they say, we don't do this stuff. We're just going to forecast. So forget about all this, like trying to figure out what the truth is. I'm not going to say that that's not a reasonable goal for a scientist. Of course, that's a reasonable goal. We just have to think about it a little bit more. That's it for now. You guys have a great weekend, and I'll see you on Monday.